Hello and welcome. We are going to look at some fundamentals of trigonometry, and these are the trigonometric ratios. I'm pretty sure many of you would be aware of these, but naturally there would also be amongst you those who are viewing this topic for the first time. For those unfamiliar, we hope this would be a good introduction to the topic. While for you who are familiar, I hope it is an enjoyable revisit to the topic as well. So trigonometric ratios are proportional relations between the sides of a right-angled triangle. To make clear, a right-angled triangle or right triangle is a triangle where two adjacent sides form a 90-degree angle between them, while the third side opposite to the 90-degree angle is known as the hypotenuse. Now you will find that, conventionally, the term right-angled triangle could be abbreviated to this or this. But since this is a bit more of a modern convention, we will be using this to describe a right-angled triangle from now on. So in a right-angled triangle, there are three sides, A, B, and C. Let's take an angle theta in our right-angled triangle. The side opposite to theta is A, while the side adjacent to theta is B, and the hypotenuse is C. The first trigonometric ratio is defined as the sinus function, or sine for short. The sine of theta is defined as A over C, and let's call this equation 2.1. The next trigonometric ratio is the complementary angle sinus function, known as cosine or cos for short. So cos theta is defined as B over C, and let's call this equation 2.2. The final trigonometric ratio is the tangent function. This is defined as A over B. Let's call this equation 2.3. Now notice something, A over B can be written as A over C divided by B over C. We know that A over C is sine theta and B over C is cos theta. Therefore, we can say that tangent theta is equal to sine theta over cos theta. Let's call this equation 2.4 and take note of it since it is an important relation. Now let's observe some examples where the trigonometric ratios or trig ratios become relevant. We want to touch on a number of special triangle cases so that you familiarize yourself with them. These triangles are cases which you will come across often throughout math in general, and so it will be worth the while to know them properly. First, let's observe the trig ratios of the right-angled triangle of angles 30 degrees and 60 degrees. Let's take an equilateral triangle of sides 2 units in length. An equilateral triangle is a triangle where all its sides are equal in length. Now we know that the sum of the angles within a triangle amounts to 180 degrees always. So if the sides are equal, the angles too must be equal. 180 degrees equally divided by 3 would give 60 degrees. Hence, each angle in an equilateral triangle is 60 degrees. Let's now divide this triangle by dropping a vertical line down its center. A 90-degree angle will then be formed at its base. When we divide this triangle by half as depicted, the 60-degree angle at the top corner will also be halved along with the base at the bottom. So the top corner will become 30 degrees while the base will be now 1 unit long. This forms our right-angled triangle. For our right-angled triangle here, we are missing the length of one side, and that is the height of this triangle. To find this, we can use Pythagoras' theorem. For those of you who aren't sure what Pythagoras' theorem is, or who are just interested, please check out our video on Pythagoras' theorem. I will provide the link to the video in the description box below. So Pythagoras' theorem states that a square plus b square equals c square. A and B being the sides of a triangle as depicted here, and C being the hypotenuse of this triangle. So in our case, the height is a, which we need to find. So a square is c square minus b square. And 2 square is 4, minus 1 would then be 3. So the square root of 3 would be a. So there's our right angle triangle with a hypotenuse of 2 units, base of 1 unit, and the height is root 3 units long. We are going to leave it as root 3 for simplicity. And of course, the angles would then be 60 degrees, 30 degrees, and 90 degrees. Now let's analyze this triangle and find the trigonometric ratios of the triangle. We know from equation 2.1, 2.2, and 2.3 the definitions of sine, cos, and tangent theta. The sine of 30 degrees is opposite of a hypotenuse, or a over c. In this case, it is 1 over 2, or half. The cos of 60 degrees, if you notice, being adjacent to a hypotenuse, is also half. So both sine 30 degrees as well as cos 60 degrees give half. These are important relationships to note, since 30 degrees and 60 degrees tend to appear rather frequently throughout math, and half is a very convenient value to work with. Now observing the cos value of 30 degrees, it gives root 3 over 2. While the sine of 60 degrees again also gives root 3 over 2. So these two also form important relationships which will come in handy in solving math problems in general. Lastly, let's finish off by deriving the tangent values of 30 degrees and 60 degrees. The tangent value of 30 degrees, as you would know by now, being opposite over adjacent, is 1 over root 3. The tangent of 60 degrees then is root 3 over 1, being just root 3. These two are the final relationships of this right angle triangle, and of course they too will come in handy as you do more and more math problems. The next right angle triangle that we're going to look at is the 45 degrees right angle triangle. This is an isosceles triangle, so it has equal length legs. In our case, the legs have a length of 1 unit. To find the length of the hypotenuse, we again use Pythagoras' theorem, whereby the sides squared added together would give the hypotenuse squared, which in this case is c. So c squared is 1 square plus 1 square being 1 plus 1, which is 2. Therefore, c is the square root of 2, and we are again going to leave it in this form for simplicity. Now, as for the angles of this triangle, since it is an isosceles triangle, the two angles at the legs must be equal. And since it is a right angle triangle as well, the third angle is 90 degrees. So the three angles would then be 90 degrees, and the remainder 90 degrees will have to be divided by 2, making them 45 degrees each. So again, we've listed equation 2.1, 2.2, and 2.3 for ease of reference. The sine of 45 degrees is the opposite of a hypotenuse, being here 1 over root 2. The same is observable for cos 45. So we can say that sine 45 is equal to cos 45. This is a very important relationship to note. Finally, the tangent value of 45 degrees can be easily read off as 1 over 1 being just 1. So what a beautiful relationship. Tangent 45 degrees equals 1. All three relations here, sine, cos, and tangent 45 degrees, are important. So please note them as they will come in handy throughout math. So to summarize, considering a right angle triangle, sine theta is opposite of a hypotenuse, being a over c. Cos theta is adjacent over hypotenuse, being b over c, and tangent theta is opposite over adjacent, being a over b. The sine value of 30 degrees is half, and this is the same for cos 60 degrees. On the other hand, cos 30 degrees equals sine 60 degrees, both being root 3 over 2. Tangent 30 degrees equals 1 over root 3, while tangent 60 degrees equals root 3. Sine 45 degrees equals cos 45 degrees, both being 1 over root 2. And finally, tangent 45 degrees is 1. And that wraps up our topic of the day on trigonometric ratios. I hope you enjoyed this lesson, and we wish to see you again in the next session. Thank you until then.